Okay, let's get rolling. Questions on 3.1? Yes, John.
On number 17, after you find the F1 of X and you figure it all out.
You mean F prime of X?
Yeah, F prime of X. And it comes out to be 0. Then the book use like the domain to find the.
Well, if you're going to sketch a graph, you always want to look at the domain, right? For the sketch part, because the domain will tell you where the graph will never go.
Okay.
And of course, that's important. Like, it might be an asymptote, or it might be a hole. So I'm sorry. Continue.
I was just wondering, like.
Why do they do the domain?
Yeah.
I would just say anytime they ask you to do a graph, and I think this one ended up with the directions, sketch the graph. Yeah. You always want to take a peek at domain. And in this case, there's an obvious domain problem. You cannot ever have that thing under the root be negative. So therefore, x squared has to be 1 or bigger. And so when x squared is less than 1, that's going to be not in the domain. And sure enough, I think that particular graph has a hole in the center. In fact, it just happens to be the one I've got up right now. And you notice there's no graph between here and here. So why did they do domain? That's why. Yeah. I didn't spend any time on domain last time, but we should be pretty familiar with it. Is that the rest of your question?
Yeah.
Okay. Other questions on 3.1? Go ahead.
Can we go over how to find the y-coordinate for graphing? Because
anytime you want to find a y-coordinate, just use the equation. So like, for example, number 17, if you want to know the y-coordinate when x is 3, just plug in 3 for x and do the arithmetic. That's basically it, just substitution. That'll give you the y. Anyone else? All right, let's, well, today is about, I don't have a very nice title here. You can tell in the book it's called Extrema and the First Derivative Test. I never put a title slide up here. Let me first explain. You all know the word extreme. In Extrema is kind of the Latin way of writing the plural of extreme. So instead of saying extremes, we say extrema. It's kind of like data is really the plural of datum. So a lot of times in Latin, the plurals just end in that A. So anyway, there's nothing other significant. So we're going to be talking about extremes. Here's what we mean by that. And you're going to hear the word relative extrema, as you see on the screen here. When a graph goes up and down, it's got these, I don't know, I guess you could call them humps, and there's going to be some where it reaches a relative high point and others where it reaches a relative low point. Together, those are called relative extrema. So, I should just sketch that. So you got a graph that, and it's got these little highs and lows. Like here's a relative extreme, this is a relative maximum, here's a relative minimum, here's a relative maximum, here's a relative minimum, here's a relative. The reason we call them relative is obviously, I call this a relative minimum here. Let me write that down. What I mean is, the reason I used relative is that's certainly not the low point of the graph. I mean, it's lower over here. but we call it a relative, meaning for that little portion of the graph, it's a low. Now, then later you're gonna hear the word absolute extrema. Well, now we mean the absolute high and the absolute low. Well, now the absolute minimum, the way from this ugly looking graph I drew here, would be over here, because that's the absolute lowest it ever gets. The absolute maximum looks like it's this one. So we're going to be talking about absolute, meaning over the whole interval, or just these relative humps, relative maximum, minimum. We're going to be using those two terms. So I guess these definitions are sometimes not worth it, but I put it up here because I thought we could take a look at it. It says a relative maximum over an interval means that it's the highest of all the other ones. Duh. It's the highest point for that particular section of the graph. And a relative minimum is for in the vicinity, it's the lowest. That's all there is to it. Now, what do you know? Anytime a graph reaches the top of a hump or the bottom of a hump, what from a slope point of view has to happen? I mean, you can't go over a hump without at least one place in that hump having a slope of 0. Yeah, otherwise it can't, I mean, if it never gets a slope of 0, it can't turn the other way. So guess what we're going to be doing? Again, we're going to be finding first derivatives and finding out, just like you did for today. Didn't you do that, where you had to set the first derivative equal to 0 and find out when that happened? And what did we call those? We call those critical numbers. Along with what else qualified as a critical number? Do you remember so this would have been quiz material for today. So the other thing is, yeah, and a way of saying that is like when the function's undefined. Asymptotes, correct. So critical numbers include two things. Either when the function doesn't exist, and maybe we have an asymptote or a hole. I think I just said asymptote. Okay, but anyway, you got an asymptote or a hole. And then the addition is, that's a new one, huh? Make sure you get that in your notes. That'll be on the test. And then the other one was when the tangent is horizontal, meaning the first derivative is equal to 0. So that's kind of a little review. Okay. So in one way, I don't have a lot new to tell you. But now, here's an interesting question. If the tangent line is horizontal, all right, we know we have a critical number, but is it a relative minimum or a relative maximum? So in other words, is it the top of a hump, or might it be the bottom of one? Now, the book goes about, so one thing you're going to have to do is figure that out. There's a couple ways to do it. You could plot some points and find out, but that's kind of a crude, slow way. The book shows a way, and they say, all right, well, I'll tell you what, let's go either side of it and see if it's got a positive, so for example, all right, we got a horizontal asymptote. Let me just, let's say we've got one, I don't know, right here on a graph, okay? But we don't know if that's a low or a high. So what you could do is go left and right and find out what the tangent is to the left of that. Maybe you find out it's increasing, and to the right of it it's decreasing. Well, you can see it's the top of a hump now. Okay, now there's a way coming in the next lesson that I think is so much better than this that I just can't wait to tell you, so I'm going to tell you today. Okay? I mean, it's like, it's a little, I just feel like today it's a little bit of a waste of time if I don't. Now, but you may look at it, there's a trade-off. It's better, and in some ways it's harder. But I think the better outweighs the harder. And that's why I'm going to tell you. I'll explain. What you can do is also calculate the second derivative. So you've already got f prime of x. go ahead, take a few minutes and find f double prime of x. And if f double prime of x at your critical value you already found, if f double prime of x is positive, it tells you the graph is concave up, which means, oh, you've got a relative minimum. Now, how do I know which? Or if f double prime of x is negative, notice I don't even care what the number is. If it's positive, it's concave up. If it's negative, it's concave down. Now you'll know if that critical point you have is a relative max or a relative min. Is it all right if I use those? I mean, I suppose if I already used asymptotes, I ought to be able to use relative min and max. Okay. Well, so now the book waits till the next lesson, where they call the next lesson 3.3 concavity and the second derivative test. Oh, it's just so exciting. I can't wait to tell you, so I'm going to tell you. I'm telling you today. All right, so here's the good news. In the book, to do it their way, they say find the critical numbers and make a table. Go one side of it, check out the first derivative, go the other side, and then you can make a deduction. And, okay, that's all right. I'm saying you don't need a table. You got your critical number. Just find the second derivative and find out if it's positive, you know it's the bottom of a hump, and if it's negative, you know it's the top. And the good news is it's less writing, maybe, and the bad news is you got to find a second derivative, and sometimes it might be a tough derivative. But I mean, they haven't. Generally speaking, the ones they've given you aren't that tough. So, I mean, yeah. If you look, for example, look at the functions from today. The functions from today were not that terribly complicated. I mean, I didn't see a lot of nesting going on, so you had to use the chain rule 5 or 6 times or anything like that. Compared to some derivatives we've done, and there's a reason for that. They want you to sketch these things, and they don't want to get too wild. And we're going to get a few new shapes in here, but graphing, we want it to be something that's, you're going to find that graphs generally, they're not going to give you real hard ones. Yeah, so here's their long way. Here's what they say. Okay, if you want to check out from A to B on the axis, if we've got a relative maximum or min, if the first derivative is negative to the left of it, okay, so what does that look like? Again, I'll make a sketch. You got your thing here. To the left of it, it's negative. To the left of it, it's negative, going downhill from left to right. And to the right of it, it's positive. Oh, guess what? I think we're at a low. And then it says relative min. Okay? So they're saying, find your critical points and look to the left, look to the right, stand up, sit down, fight, you know. And I'm saying, instead of doing that, let's find the second derivative, and we'll be able to tell that way a little more quickly. So even though I wanted to show it to you, we're going to kind of bypass this chart. So here's what they're saying. Well, if this has got a derivative of 0, we know it's either a high or a low. If it's coming down on the left and going up on the right, duh, we got a low. The duh you'll have to write in. I didn't put that up here. Or here, if to the left of it it's positive and to the right of it it's negative, duh, we're at a high. That's all that stuff is saying. Now, it could happen that you've got this. If it's going up to the left and up to the right, now it's just kind of a resting spot. It's not a relative min or a max. And we have a name for this. I wrote it in on the bottom. Even though the book, I don't think, has said it yet. Yeah, it comes a little bit later, page 194. This is called a point of inflection, or just inflection point. So, relative max, relative min, inflection point. So it's like not a high, it's not a low, it's just kind of a, we'll take a time out here. We're changing from one to the other. We're changing from a curve down to a curve up, inflection. Or changing from a concave up to a concave down. By the way, I never told you this, but what do you think happens if you take the second derivative at one of these inflection points? I already told you what happens here. Second derivative here, positive concave up. Second derivative at this point is going to be negative because it's concave down. What do you think it's going to be here at an inflection point? The second derivative will be right kind of in between, 0. So when a second derivative comes out to 0, you go, aha, you got an inflection point. Again, you're not going to find this in the book until the next lesson. But it just makes sense you should use this tool right away. Terminology. Here we have a curve, a generic curve over an interval from A to B. This point right here is a relative maximum. It's not the highest point of the whole curve, obviously, right? But for this, vicinity, this is a high. So we call it a relative max. Here we have a relative min. Here we have an absolute max, meaning from the period from A to B, this is the highest value y will be. And this one is not only a relative min, but isn't it the absolute min? Over the whole A to B, isn't that the lowest? So you get the difference between relative and absolute terminology that we'll be making use of. Okay, so how do you find absolute extrema? Well, first of all, let's go back. How do you find relative extrema? Actually, I'll give you a hint. I taught you how to do it yesterday. Mostly. What did we learn? How do you find out when something has reached either a high or a low? Review. From a calculus point of view, what's true of a curve that reaches a part up on top like this? Won't its tangent have to equal 0 sometime? So what did we do yesterday, and what are we going to be doing again today? We're going to be calculating the first derivative and finding out when it's 0. And didn't we did that for today, right? Find the first derivative, set it equal to 0, and solve. Okay. Now, here's the new part. How will you know if it's the top of a hump or the bottom? How will you know if it's a relative max or a min? You could use their technique, go either side, but I'm saying go ahead and calculate the second derivative and just repeat. If the second derivative value at that number, at x equals whatever you found was the critical point, if that comes out to a positive, we say the curve is concave up, and now you know that has to be a minimum. If the second derivative value is any negative number, now you know it's concave down, we call that, and therefore that critical thing has to be a relative max. Okay, so that's kind of the main thrust. So what is this? So how can you find absolute max then? All you got to do is one additional thing. You've already found all the absolute mins and maxes. How do I find the absolutes? The answer is just check the endpoints. So let me just go back. Remember on this graph, if you do what I just said, you're going to find this and this, the relative min and the relative max. What do you have to do additionally to find the absolute min and max? And the answer is keep these in mind, but also check it at the endpoints. Check how high it is at value A, and check how high it is at value B. How do you do that? You substitute it in, and you get the y coordinate. Which one is the absolute highest? That's your absolute. Which one's the absolute lowest? Now in this case, do you see how one of them served two purposes? This was both a relative minimum and an absolute minimum. So, okay, well, let's get in there and do a problem or two. Page. So please note, in the book, you're going to see all these tables. And I'm kind of avoiding the tables. There's nothing wrong with them. I just figure, hey, we're going there tomorrow. Why not go to there today? So here we go. Yeah. So you're going to have to ignore some directions, like numbers 1 through 4. It says in the book, use a table. And I've just told you, no, you don't have to do that. But let's still do it. It says find all the relative extrema. So, number 1, we have negative negative 2x squared plus 4x plus 3. Once again, we're going to begin like we did yesterday. We need to find the first derivative. And that's nice and easy in this case. Now, when is that slope, or first derivative, equal to 0? And then just solve it. Okay, so we found a critical value. It looks like that's the only one, right? Is there any other solution to that? It should be it, right? I don't think so. See, what I did is I added 4x to both sides, but thank you. Okay, now, what was I trying to say here? So, x equals 1 is a critical value, but we don't know if it's a relative max or min. Actually, on the basis of algebra, you really do. What do you know from your previous algebra experience that tells you if this is a high or a low? I know you know this. Just look at the equation. Look at the top line, and I'll bet you can tell. Know anything about the shape of that, negative 2x squared? Doesn't that have to be like this? Didn't you learn that when there's a negative coefficient in front of that squared term, doesn't that mean this? Yeah. Well, if it's this, then guess what? Is it a high or a low? It's got to be a relative max. Now, all right, let's say you didn't see that. Okay, what's the second derivative? Now here's where I'm differing from the book, okay? What's the second derivative? Here's the first derivative. It's really easy, isn't it? Just negative 4. Now, do you remember what I told you a little while ago? What does that tell you when the second derivative is negative? It says concave down, which confirms what we said before. And if it's concave down, then my critical point has to be a relative. And by the way, is it only a relative max, or is it also a absolute max? It's absolute in this case. Why? Because parabolas don't start turning back up later on, right? You need like cubes where, so parabolas don't like, I'm sick of going down, I think I'll go up. Parabolas always head down. So, or if they're right side up, they always head up. Okay. Did they ask about absolutes? Actually, they didn't ask that, so we just did a little extra credit there. Okay. Let's go to do one from the second section again. Only this time, notice it doesn't say use the table. So let's take one like 11. That looks a little bit interesting. Sorry, I needed some extra pages here. Okay, so number 11. We have a few extra terms here. So this will make it a little more interesting. X to the fourth minus 2x cubed. So we want to find the critical values. By the way, from a domain point of view, and I didn't do this in the last one because I thought it was pretty obvious, can there be any asymptotes here? Well, let's put it this way. Are there any values of x that will cause the system to crash? You know, like in that square root, you know you could never have a negative under it. And you know denominators are another big roadblock. You can't have a zero. And we don't have any denominators. We don't have any roots. So it sure doesn't look like we don't have any asymptote problems here. Okay. So so where are the critical values? Answer, find first derivative. Set first derivative equal to 0. Maybe, yeah, I'll just... Okay, I didn't have, maybe I should have just left it where it was. My apologies. You could do it that way, but I think a better way is factor it. So what can I do to factor this? I could take out, what, a 2 and an x squared? Now set each factor equal to 0. Solve. What? Thank you. It's supposed to be 2x minus 3. Thank you very much. And then this comes out to, on this side, we get 2x equals 3, and x equals 3/2. So we found two places where the first derivative is 0. Therefore, these are both critical values. Now the question is, are they relative mins or relative maxes? Now the part that's different from the book. Let's calculate. Maybe you may find it's better to run the second derivative right away, by the way. Right after you do the first, maybe do f double prime, but I'll do it down here. What's the second derivative? Well, the second derivative is 12x squared minus 12x. Okay, now, what's f double prime at 0? Now, where did I get that from? I'm just taking my first critical value. What's f double prime of 0? It's 0, isn't it? What does that tell us? This is neither a relative min or a max. This evidently is an inflection point. So let's just... And by the way, like I said, I've jumped the gun a little bit because I don't think the book talks about those yet. How about this one? What's f double prime at 3/2? Well, let's see. It's going to take a little while. What's 3/2 squared? 9/4. And what's 9/4 times 12? 27. And then what's 3/2 times 12? 18. 27 minus 18 is certainly positive. Therefore, this is concave up, and this must be a relative min. Okay. Now this is cut. Did I copy that correct? X to the fourth minus 2x cubed. This is an odd. I want to look in the back and see what they did with the inflection point. Or they just do it by table. Yeah, it should agree. Did anybody look in the back? I will. That's all right. I'm just so slow at this. Where are we? 3, 2, number 11.
It says relative
It says what?
relative min.
For the other one? But what I mean is for the x equals 0, it says relative. Oh, it just says one of the points is a relative min. I gotcha. Yeah, so they don't talk about the inflection point. That's my point, yeah. So, actually, I think this answer is a little bit more complete, but do you see, you see how you got a little different opinion in the back of the book here because they haven't taught you some of this stuff yet? So just be aware of that. So, what does that mean? At x equals 0, this graph is in some state of transition. It's probably, it's at a point where it's changing from concave up to concave down or vice versa. It's some kind of a transition. But at x equals 1.5, we know it's reached a relative min. Okay, let's move on. Do they ever get to sketching in this? Let's see. Yes?
I noticed that, but
Uh-huh.
for the next step, how would you know what's the absolute value?
Oh, yeah, thanks. This would probably be a good time to do that. Okay, in order for them to ask you that question, they have to give you an interval. So, for example, this might be a good time, so we don't have to do another whole problem. What if we said the interval was, I don't know, let's say -2, I should put a closed on that, sorry. Let's say I'm just making this up now. Okay, now they might say to you, what are the absolute extrema on the interval -2, 2? Okay, this same information is very helpful. In addition to these two critical points, what other 2 points do we need to look at? Answer, the endpoints. So namely, I got to look at when x is -2, and I got to look at when x is 2. Where am I going to get that from? Answer, just plug it in and find out. So, what is f of -2? And we never did get these values either. Actually, we got to do a little bit more, but that's okay. What is f of -2? Let's see. When you square it, you've got 4, and you square it again, you've got 16. So it's 16 plus, wow, it's going to be big, isn't it? -2 cubed is -8. -8 times -2 is positive 16. 16 plus 16, it's 32, isn't it? Anybody? Did anybody do the calculation? All alone on that. Yeah, I guess. Okay, let's try it with +2. Okay, with +2, this is going to be 16, and this is going to be -16, and I'm going to get 0. Right? Now, let's also find, I got to do one more thing now. I got to find the y-coordinates for these 2 points. So, let's just go down here and finish this. 0, comma, what? That's an easy one. Right? If you plug in 0 here, 0 minus 0 is 0. Some of you guys, I'm going to have to go get the defibrillator in here or something. I'm not getting any response at all. Not a... Okay. First, we got to get the first responders in here. Is that right?
Yeah.
Just nothing, like, okay. What's this? What's the other critical value? Now, here you're going to have to help me. Let's see, what's 3/2 to the 4th? 81 over 16 minus 3/2 cubed is what? 27 over 8 times 2 is 27 over 4. So it's 81/16 minus, so it's like -19, negative 27/16. Okay, now, which one is absolutely the highest? Obviously 32 wins. So what's the absolute max? It happens at x equals negative 2. What's the absolute min? This one. So this relative min also turned out to be the absolute min. So even though this was, by the way, this was not asked in the book, but it's a good way to show you what would you do if we asked for the absolute. All you got to, number one, they've got to give you an interval. If they don't give you an interval, you can't do it, because this varies hugely if you change the boundaries. All you got to do is add the endpoints, find out what the y values are. You got to find the y coordinates of your two critical points. Throw them all together. Which one is the absolute highest? This is called look and see. Find high, and then find low. So it's not very hard to go to the absolutes. Yes.
For the coordinates on the left, you only have 3 because x equals 0 for one of them, so it would be 0, 0. I don't understand. You use first two you use.
I didn't put this one down. I should have. 0, 0 should be in the list too. So there's two relatives. I should have put them both in there. And then you put in your left boundary and your right boundary, and then look for the high and the low. Yeah. Thank you. That should have been there. Mm-hmm.
So the -2, 0, that would be called inflection.
Actually, this is the inflection point. Remember we found when x is 0? Just a point on the graph. Oh, what did we say? It's simply the right border that they chose. It's not an inflection. It's not a max. Thank you. And neither is this one. I mean, sure, it's the absolute max, but I mean it's not a special curvature point or something like that. It just happens to be. So do you see how this is absolutely important? That they got to give you boundaries, otherwise you can't do these absolutes. Because it totally changes if they give you different boundaries. Okay. Thanks. That was a good way to do that, to couple that with another problem. Did anybody look ahead? Are they asking you to do any sketching? It doesn't look that way. I think that's maybe coming next time. Okay, let's check out what the assignment is. By the way, you probably get the graphic that I put up here now. Maybe if anybody look at that, do you see why I chose that graphic? Because what does it have circled? Relative max and min, yeah. Relative extrema. And absolute, there's an absolute up there. So there's 3, 2. We're doing that every other odd thing again, the 1, 5, 9, ... 37. Can you give me your assignment from today? Cool. Just have